Proving that bacteria can actually digest plastic requires a 4-month endurance test. Over those 120 days, 3 silent threats can ruin your data: liquid quietly evaporating from your flasks, cellular biofilm adding false weight to the plastic, and cross-contamination from the lab environment. This checklist shows the core materials you need to mitigate those risks from day one. You will require an analytical balance, your pre-cut plastic samples, minimal salt medium, or MSM, sterile breathable sealing film, and a 2% SDS solution. Because you are incubating for a third of a year, a tiny procedural error in week 2 becomes a massive data failure in week 16. Mastering strict fluid management and cleaning protocols is the only way to generate degradation data that holds up to scientific scrutiny. Step 1 is preparing your plastic. Wash the pieces thoroughly in 70% ethanol to strip away factory residues or transient microbes, and then let them dry completely. Next, take the initial weight of the dry plastic using the analytical balance. This number is your baseline. If there is even a microscopic layer of moisture left on the plastic, it will inflate this starting mass and skew your final results. Under a sterile hood, you assemble your assay. Pour in the minimal salt medium, drop in the plastic pieces, and inoculate the liquid with your chosen bacteria. The SMM provides essential nutrients, but no carbon. By making the plastic the sole carbon source, you force the bacteria to eat it or starve. Cover the flask with a sterile, breathable sealing film. This membrane allows oxygen to flow freely in for the bacteria, while blocking moisture from escaping. Balancing oxygen intake against moisture retention sets the foundation for a successful assay. Now that the flask is sealed, move it into an orbital shaker incubator. You'll set this machine to maintain a continuous, optimal temperature and an exact rotational speed to keep the culture aerated. A continuously heated and agitated incubator guarantees rapid fluid evaporation over 4 months, no matter how well you sealed the flask. Every 20 to 30 days, pull the flask from the incubator, place it under a sterile hood, and extract the old liquid medium. Immediately replace with fresh, sterile medium. This restores your original baseline. This split-screen diagram illustrates why. On the left, bacteria metabolizing plastic release toxic byproducts that accumulate. On the right, our fluid exchange flushes those toxins out. Proactive media replenishment guarantees the microbial culture stays healthy and actively mineralizes the polymer, rather than dying off in its own waste before the assay finishes. At the end of the 120 days, it is time to harvest. When you extract the plastic pieces, you will notice a thick, cloudy layer of bacterial biofilm clinging to the surface. Do not put this sample on a scale. This is the false weight trap. If you weigh the plastic right now, the accumulated cellular mass will incorrectly show that your sample gained weight, hiding any actual degradation. To reveal the truth, use a 2% SDS solution. The SDS chemically strips the plastic, rapidly breaking down and dissolving that stubborn cellular debris. After the SDS treatment, wash the pieces thoroughly with distilled water. This rinses away the residual chemicals, leaving you with nothing but the pure, stripped polymer. Aggressively debiofilming your sample is mandatory. It ensures your final mass measurement isolates the degraded polymer itself, completely free of microbial weight. Before heading back to the scale, place the stripped plastic into a 50-degree oven. You must leave it there until it reaches an absolutely constant, moisture-free state. Now, place the completely dry plastic on the analytical balance. Record this final weight. If the bacteria did their job, this number will be lower than the baseline you recorded 4 months ago. To quantify the drop, use the weight loss percentage formula: initial weight minus final weight divided by initial weight multiplied by 100. For example, a 100 milligram starting sample weighing 82 milligrams at harvest shows an 18% degradation rate. By meticulously managing evaporation levels and chemically stripping the false weight of the biofilm, you turn a chaotic 120-day incubation into hard, defensible data. And with the sample clean and dry, it is perfectly prepped for advanced analysis like SEM surface scanning or FTIR spectroscopy.